Picture this. A single second in the darkest corner of space unleashes more energy than our Sun will produce in its entire 10 billion year lifetime. This isn't science fiction. This is a gamma-ray burst, the universe's most violent explosion since the Big Bang itself. And when one of these cosmic monsters goes off at the edge of the known universe, it becomes a beacon shining across 13 billion years of cosmic history. Gamma-ray bursts are nature's ultimate fireworks. In less time than it takes to blink, they outshine entire galaxies, but the most distant ones, those are special. They're like messages in a bottle from the universe's childhood, carrying secrets about how the first stars lived and died. Today we're going on a journey to the farthest reaches of space and time. We'll explore 50 astonishing facts about these distant cosmic explosions. You'll discover how they act as time machines, why some vanish without a trace, and how they might have created the gold in your jewelry. We'll meet record-breaking bursts that defy physics, mysterious dark explosions that leave astronomers scratching their heads, and even one that was briefly visible to the naked eye from Earth. By the time we're done, you'll understand why gamma-ray bursts are the universe's most fascinating mystery. So buckle up. We're about to travel further than any telescope can see, back to the cosmic dawn itself. The journey starts now. Now, let's zoom in on the very edge of the observable universe where time itself seems to bend. The title for the most distant gamma-ray burst ever detected goes to GRBs 090423, a cosmic explosion so far away its light took 13 billion years to reach us. That's not just a number, it's a time machine. When this burst erupted, the universe was a mere 600 million years old, still in its infancy. What makes this distance measurable is something called redshift, a stretching of light waves as the universe expands. GRBs 090423 has a staggering redshift of 8.2, placing it among the earliest cosmic events we've ever witnessed. To put that in perspective, this burst happened before Earth existed, before the Milky Way took shape, even before most stars had finished lighting up the darkness of the early cosmos. Detecting something this ancient isn't just about breaking records. It's like finding a fossil from the universe's first chapter. The light from GRB 090423 carries clues about the conditions of the primordial cosmos, how hot it was, how dense, and what kinds of stars were dying to create these spectacular explosions. Every photon from this burst is a messenger from an era when the universe was still figuring out what it wanted to be. And here's what's truly mind-blowing. When this burst occurred, the universe was so young that the first galaxies were barely forming. The fact that we can see it at all is a testament to both the incredible power of gamma-ray bursts and the ingenuity of the telescopes that catch them. GRB 090423 isn't just a distant explosion, it's a window into a time when the cosmos was taking its very first breaths. Now, let's peel back another layer of this cosmic mystery. Gamma-ray bursts aren't just flashes in the dark, they're time capsules, carrying secrets from the universe's earliest days. Think of them as ancient letters written in light, traveling billions of years to reach us. Every photon from a distant burst is a snapshot of conditions long gone, frozen in time the moment it left its source. Take star formation, for example. The light from these bursts passes through clouds of gas and dust on its journey, absorbing fingerprints of the elements it encounters. By studying these absorption lines, astronomers can calculate how many stars were being born in the early universe. It's like reading a cosmic census report from an era when galaxies were just beginning to take shape. Then there's the metal content, or rather, the lack of it. In astronomy, anything heavier than hydrogen and helium is called a metal, and distant GRBs reveal something surprising. The early universe was metal poor, meaning the first stars were made of almost pure hydrogen and helium. These pristine giants burned hot and fast, leaving behind traces in the light of GRBs that help us piece together the chemistry of the cosmos in its youth. But here's the real kicker, because gamma-ray bursts are so bright they outshine their host galaxies, giving us a clear view of the environment around them. Unlike quasars, which are buried in the glare of their own galaxies, GRBs act like cosmic flashlights, illuminating the gas and dust between us and the burst. This lets astronomers map the structure of the early universe in ways that would otherwise be impossible. So the next time you hear about a distant gamma-ray burst, remember, it's not just an explosion. It's a time machine offering us front-row seats to the universe's most formative moments, and with each new detection, we're rewriting the story of how everything came to be. Now, let's zoom in on the cosmic powerhouses behind these spectacular bursts. Long-duration gamma-ray bursts don't just happen randomly, they're the dramatic final acts of massive stars, the true titans of the universe. Picture a star so colossal it makes our sun look like a speck. These giants burn through their fuel at an astonishing rate, living fast and dying young in cosmic terms. Here's how it works. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity, triggering a supernova. But in some cases, the collapse doesn't stop there. Instead, it forms a black hole or a rapidly spinning neutron star, launching jets of material at nearly the speed of light. These jets, focused into narrow beams, punch through the star's outer layers and blast into space, creating the gamma-ray burst we detect billions of years later. What makes this even more fascinating is the timeline. These massive stars have lifespans measured in mere millions of years, a blink compared to stars like our Sun, which shine for billions. That means when we detect a distant gamma-ray burst, we're likely witnessing one of the universe's first stellar deaths. These explosions happened when the cosmos was still in its infancy, offering us a rare glimpse into the chaotic early days of star formation. And here's the kicker. Because these stars were made of almost pure hydrogen and helium, lacking the heavier elements forged by earlier generations, their deaths were even more violent. No metals meant weaker stellar winds, allowing the stars to retain more mass until their explosive ends. The result, even more powerful gamma-ray bursts, lighting up the early universe like cosmic fireworks. So the next time you hear about a long-duration GRB, remember, it's not just an explosion. It's the final scream of a massive star that lived fast, died young, and left behind a beacon of light that's traveled across the ages to tell its story. Now, let's unravel another layer of the gamma-ray burst mystery by comparing the two main types, short and long bursts. While long GRBs steal the spotlight in the distant universe, their shorter counterparts tell a different story. Short gamma-ray bursts, lasting less than 2 seconds, are cosmic flashbulbs triggered by the violent mergers of neutron stars or a neutron star colliding with a black hole. These events are like the universe's ultimate smash-ups, releasing intense energy in a fraction of the time it takes to blink. But here's where things get interesting. When we peer deep into the cosmos, hunting for the most ancient bursts, we almost always find the long-duration variety, the ones tied to the deaths of massive stars. Why? Because short GRBs rely on neutron star mergers, which take time to happen. Neutron stars are the dense remnants of earlier stellar generations, meaning the universe needed to cook up stars, let them live, die, and then have their leftovers spiral together over billions of years. In the early universe, there simply wasn't enough time for that cosmic dance to play out. This imbalance gives us a clue about the demographics of the infant cosmos. The dominance of long GRBs at extreme distances paints a picture of a universe teeming with massive, fast-living stars. Stars that blazed through their fuel and exploded before their smaller, longer-lived siblings even had a chance to settle in. It's like finding a fossil record where only the giants left their mark. So while short bursts illuminate the modern universe's compact object collisions, long GRBs are our window into the past, revealing an era when colossal stars ruled the cosmic landscape. Each type tells a different chapter of the universe's story, but it's the long bursts that carry the whispers of the dawn of time. Now, let's step even further back in time, to an era so ancient it's often called the universe's Dark Ages. This mysterious period stretches from just after the Big Bang to the moment the first stars flickered to life, a time when the cosmos was shrouded in a thick fog of neutral hydrogen gas. No stars, no galaxies, just darkness. But here's the incredible part. Gamma-ray bursts are like cosmic flashlights piercing through that primordial gloom. When a distant GRB erupts, its afterglow, the lingering light that follows the initial blast, travels through this early hydrogen soup. Along the way, that light gets imprinted with the fingerprints of the gas it passes through. Astronomers can read these fingerprints, using them to map the distribution and density of hydrogen clouds across the universe. It's like turning the GRB into a backlit probe, revealing the invisible structures of the infant cosmos. What makes this even more groundbreaking is how these bursts help us witness the universe's great transformation, the epoch of reionization. As the first stars and galaxies ignited, their intense radiation began to ionize the surrounding hydrogen, tearing electrons from atoms and slowly clearing the cosmic fog. GRB afterglows capture this transition in action, showing us patches of the universe where the gas is still neutral versus areas where it's become transparent. Think of it as uncovering a cosmic fossil record, but instead of digging through layers of rock, we're decoding layers of light. Each distant GRB peels back another veil, giving us a front-row seat to the universe's earliest chapters, a time when darkness gave way to light and the stage was set for everything we see today. But here's something that will truly bend your mind. Gamma-ray bursts don't just illuminate the early universe, they outright dominate it in raw power. Picture this, in just a few seconds, a single GRB can unleash more energy than our entire Milky Way galaxy emits over centuries. Take GRB 080916c for instance. This cosmic monster released a staggering 5 times 10 to the 54 ergs of energy. To put that into perspective, our Sun, a blazing ball of nuclear fusion, will spend its entire 10 billion-year lifespan radiating less energy than this one burst did in a heartbeat. It's almost impossible to fathom that scale. Imagine every star in 100 galaxies, every supernova, every flicker of light across eons, all outshone by a single fleeting event. GRBs aren't just bright, they rewrite the rules of cosmic extremes, and the most distant ones, their light has traveled so far for so long that by the time it reaches us, it's a whisper of that original cataclysm. Yet even that whisper carries enough punch to outmatch nearby galaxies in our telescopes. What's even wilder is how efficiently GRBs channel this energy. Unlike a galaxy's light, which sprays in all directions, GRBs focus their fury into narrow jets moving at nearly the speed of light. That's why, even from billions of light years away, they can briefly outshine everything else in the gamma-ray sky. It's like comparing a laser pointer to a light bulb. The GRB's precision turns mind-boggling energy into a beam so intense it defies belief. So the next time you look up at a starry night, remember, somewhere out there, a GRB could be detonating with the force of 1,000,000 suns, etching its name into the record books of the cosmos, and we're here to catch every earth-shattering moment. Now let's shift our gaze from the raw power of these cosmic explosions to the unsung hero that helps us study them: NASA, a swift satellite. While GRBs themselves are fleeting, often lasting just seconds, their afterglows can linger for hours or even days, offering a golden opportunity for scientists to study them. But here's the catch: these afterglows fade fast, and if you're not quick enough, you'll miss them entirely. That's where SWIFT comes in. This nimble spacecraft is like the universe's quickest detective, designed to do one thing exceptionally well: slewing or turning rapidly to point its instruments at a GRB the moment it's detected. Imagine a security camera that can snap to attention the instant a crime happens, and you've got the idea. SWIFT doesn't just sit and wait, it's constantly scanning the skies, and when it spots a burst, it can pivot in less than a minute to lock onto the target. That speed is absolutely critical because every second counts when you're racing against the fading light of an afterglow. Since its launch in 2004, SWIFT has detected hundreds of gamma-ray bursts, including some of the most distant ones ever recorded. Its ability to catch these events in real time has revolutionized our understanding of GRBs, turning them from mysterious flashes into rich sources of data. And it's not just about speed. SWIFT carries a suite of instruments that work together to study the bursts across different wavelengths, from gamma rays to visible light. This multi-wavelength approach lets scientists piece together the full story of each explosion, from the initial blast to the lingering aftermath. So while GRBs might be the universe's most dramatic fireworks, it's missions like SWIFT that give us a front-row seat to the show. Without this satellite's lightning-fast reflexes, much of what we know about these distant bursts would still be hidden in the dark. But SWIFT isn't the only eye in the sky keeping watch for these cosmic explosions. Let's talk about another game-changer, the Fermi Gamma Ray Space Telescope. While SWIFT specializes in speed, Fermi brings something else to the table, an unmatched ability to detect the highest energy photons in the universe. And in 2009, it made history with GRB 090902b, a burst that shattered expectations. This particular GRB unleashed a photon with an energy of 33 gigaelectronvolts, the most energetic photon ever recorded from a gamma-ray burst. To put that in perspective, that's billions of times more energetic than visible light. But here's where it gets even more fascinating. According to our models, photons this energetic shouldn't survive their journey across the universe. The cosmic microwave background, the faint glow left over from the Big Bang, should absorb them long before they reach us. Yet Fermi caught this one red-handed, forcing scientists to rethink how high-energy light interacts with the fabric of space. What does this mean for our understanding of GRBs? For starters, it suggests that these explosions are even more powerful than we thought, capable of producing extreme energies that defy conventional physics. It also hints at gaps in our knowledge about the early universe's conditions. If photons like this can slip through, maybe the cosmos was more transparent to high-energy radiation than we assumed. Fermi's discovery didn't just add another record to the books, it opened a new chapter in GRB research, proving that these distant flashes still have surprises up their sleeves. And with every anomaly they uncover, telescopes like Fermi push us closer to unraveling the universe's biggest mysteries. Now, let's turn our attention to a puzzling twist in the GRB story, the enigma of so-called dark gamma-ray bursts. These are the bursts that play hard to get, vanishing without a trace after their initial flash. Unlike their more cooperative counterparts, roughly 20 to 30% of GRBs leave no detectable afterglow, making them far trickier to study. So what's going on here? One leading theory points to cosmic dust. Imagine a GRB erupting in a galaxy packed with thick clouds of dust. Those particles could absorb the afterglow's light before it ever reaches us, effectively hiding the burst's true nature. Another possibility is that the jet of energy simply isn't aimed in our direction. GRBs beam their radiation in narrow cones, and if Earth happens to be outside that cone, we might catch the initial blast but miss the lingering glow. This absence of afterglows isn't just a minor inconvenience, it's a real headache for astronomers trying to measure distances. Without that fading light to analyze, pinning down how far away these bursts occurred becomes a guessing game. Some dark GRBs might actually be among the most distant events in the universe, but without the afterglow's telltale fingerprints, we can't say for sure. Yet even these elusive bursts have their secrets to share. By studying the ones we can detect, scientists are piecing together clues about the environments where GRBs occur. Are dark bursts more common in dust-filled galaxies? Do they favor certain types of stars? Each missing afterglow is a cosmic riddle, pushing researchers to refine their tools and theories. And as telescopes grow more sensitive, the veil over these dark GRBs may finally start to lift. Now, here's something that might surprise you. Gamma-ray bursts aren't just cosmic fireworks, they're also some of the universe's most prolific goldsmiths. That's right, these explosive events play a key role in forging heavy elements like gold, platinum, and uranium through a process called rapid neutron capture, or R-process nucleosynthesis. When a massive star collapses or neutron stars merge, the two main triggers for GRBs, the extreme conditions create a neutron-rich environment where atoms can grab free neutrons at an astonishing rate. This rapid capture builds up heavier and heavier elements in a matter of seconds, filling the cosmos with precious metals that would otherwise be incredibly rare. What's even more fascinating is that the most distant GRBs might have been the universe's first heavy element factories. In the early cosmos, before generations of stars had time to spread metals through space, these bursts could have been the primary source of elements like gold. That means the ring on your finger or the platinum in your electronics might trace its origins back to a cataclysmic explosion billions of years ago. But here's the twist: not all GRBs contribute equally. Scientists suspect that short bursts, often linked to neutron star mergers, are the real champions of R-process creation. Meanwhile, long bursts from collapsing stars might produce fewer heavy elements. By studying the afterglows of distant GRBs, researchers are piecing together how these cosmic forges shaped the chemical makeup of the early universe and, ultimately, the building blocks of planets and life itself. So the next time you hear about a gamma-ray burst, remember, it's not just a fleeting flash of light. It's a cosmic alchemist turning the raw ingredients of the universe into the very elements that make our world and even us possible. Now, let's unravel one of gamma-ray bursts' most intriguing puzzles, the Amati relation. This cosmic rule of thumb connects a burst's total energy to its peak brightness, acting like a fingerprint that helps astronomers classify GRBs. Picture it as a cosmic speedometer. The faster a burst's light fades, the more energy it likely packed. Most long GRBs follow this pattern neatly, like well-behaved students in a physics classroom. But then there's the rebel GRB 060614. This burst broke all the rules. It had the duration of a long GRB but lacked the telltale supernova and didn't fit the Amati relation's energy expectations. It's like finding a whale that barks instead of sings. This oddball forced scientists to rethink their playbook, suggesting some GRBs might spring from entirely different cosmic catastrophes, perhaps even exotic mergers we've yet to understand. What makes the Amati relation so valuable and its exceptions so thrilling is how it acts as a cosmic litmus test. When a burst defies it, like GRB 060614 did, it's not just a fluke. It's a flashing signpost pointing toward gaps in our knowledge, hinting at new physics or unseen stellar phenomena. These outliers remind us that the universe loves to throw curveballs, and gamma-ray bursts, especially the distant ones, are its favorite pitch. So while the Amati relation helps us sort GRBs into tidy categories, it's the rule breakers that keep astronomers on their toes, proving the cosmos still has plenty of secrets left to spill. Now, let's shine a light on the incredible teamwork that makes unraveling gamma-ray bursts possible. When a distant burst lights up the cosmos, it's not just one telescope that springs into action, it's an entire fleet of observatories working in perfect harmony. The Hubble Space Telescope, the Chandra X-ray Observatory, and powerful ground-based telescopes like the Very Large Telescope in Chile join forces like a cosmic detective squad. Hubble's sharp eyes capture the faint afterglow in visible and ultraviolet light, while Chandra zeroes in on the high-energy X-ray emissions. Meanwhile, ground telescopes use spectroscopy to dissect the afterglow's light, hunting for telltale fingerprints like hydrogen absorption lines. These clues reveal the burst's redshift, letting astronomers calculate its mind-boggling distance. This collaboration is crucial because no single telescope can do it all. Hubble might spot the afterglow, but without Chandra's X-ray vision or ground telescope's spectroscopic precision, we'd miss the full story. It's like piecing together a puzzle where each observatory holds a critical piece. Together, they transform a fleeting flash of gamma rays into a detailed cosmic map, showing us not just where these bursts occur, but also what the universe was like billions of years ago. The next time you hear about a record-breaking gamma ray burst, remember, it's not just a single discovery, it's a triumph of teamwork where the world's greatest observatories unite to decode the universe's most distant explosions. Now let's zoom in on one of the most clever tricks astronomers use to measure the mind-bending distances of gamma ray bursts, the Lyman break technique. Picture this: when light from a distant GRB travels across the universe, it doesn't arrive untouched. It passes through clouds of hydrogen gas, and these clouds leave a unique fingerprint on the light. Here's how it works. Hydrogen gas loves to absorb light at a specific wavelength around 121.6 nanometers in the ultraviolet range. But here's the catch: as the universe expands, that light gets stretched or redshifted, shifting it toward longer wavelengths. Astronomers look for the exact point where the GRB's light suddenly drops off the Lyman break, because that tells them how much the light has been stretched. Think of it like listening to a song played at different speeds. If you know the original pitch, you can figure out how much the recording has been slowed down by hearing where the notes change. The Lyman break does the same thing with light. By pinpointing where the drop-off happens in the GRB's spectrum, astronomers can calculate its redshift and from there its distance. This technique is especially powerful for the most distant bursts, whose light has traveled so far that the Lyman break shifts into the visible or even infrared part of the spectrum. Without this method, we'd be missing a key tool for mapping the universe's earliest epochs. So next time you hear about a GRB billions of light years away, remember, it's not just about spotting the burst, but reading the hidden clues in its light. Now let's shift our focus to another cosmic heavyweight, quasars, and see how they stack up against gamma-ray bursts as windows into the early universe. Both GRBs and quasars are brilliant beacons in the darkness, but they shine in very different ways. Quasars are the blazing cores of distant galaxies, powered by supermassive black holes gobbling up matter. They're incredibly bright and can outshine entire galaxies for millions of years. But here's the catch: their light comes from the chaotic mess of materials swirling around the black hole, which means it's often muddled by the glow of their host galaxies. This makes it harder to pick apart the pristine signals from the early universe. GRB, on the other hand, are like cosmic flashbulbs, brief, violent, and blindingly bright. They cut through the noise because their light isn't drowned out by their host galaxies. Even if a GRB happens in a faint, distant galaxy, its afterglow can be studied in isolation, giving astronomers a cleaner look at the conditions of the early cosmos. Another key difference: rarity. Quasars are relatively common compared to GRBs, but GRBs punch deeper into the universe's past. Some of the most distant quasars we've found date back to when the universe was around 700 million years old. GRB, like GRB 090423, take us even further, just 600 million years after the Big Bang. So while quasars are steady lighthouses, GRBs are fleeting but piercing searchlights. Together, they give us complementary tools to explore the universe's darkest corners. Next time you hear about a distant quasar or GRB, remember, each has its own unique way of revealing the secrets of our cosmic dawn. Now let's unravel one of the great cosmic puzzles: why so many distant gamma-ray bursts seem to come from small, faint, and oddly shaped galaxies. You'd think the most powerful explosions in the universe would happen in the biggest, brightest galaxies, right? But nature loves to surprise us. These host galaxies are often irregular, messy, chaotic, and nothing like the neat spirals or smooth ellipticals we're used to seeing. And here's why that matters. These scrappy little galaxies are stellar nurseries on overdrive. They're packed with gas, low on heavy elements, and buzzing with frantic star formation. That's the perfect recipe for creating the kind of massive, fast-burning stars that end their lives as gamma-ray bursts. Think of it like this. In a quiet, orderly neighborhood, you might not see much action. But in a bustling, chaotic city, things explode into life literally. These irregular galaxies are the cosmic equivalent of that energetic city. Their low metal content, meaning fewer elements heavier than hydrogen and helium, let stars grow bigger and burn hotter. And when those stars collapse, they're far more likely to produce the narrow, ultra-powerful jets that give us GRBs. Even more intriguing, these galaxies are so faint that without the GRB's flash, we might never spot them at all. It's like using a firework to find a hidden village in the dark. Each burst not only marks the death of a massive star, but also shines a light on these otherwise invisible cosmic backwaters, helping us piece together how the universe built its first generations of stars and galaxies. So next time you hear about a distant GRB, remember, it's not just about the explosion. It's a clue pointing us to the wild, untamed corners of the early universe where the rules are different and the stars play by their own. Now, let's zoom in on a fascinating twist in the gamma-ray burst saga the moment an afterglow suddenly dims, revealing secrets about the explosion's inner workings. This is the jet break phenomenon, and it's like catching the universe in a candid moment, letting its guard down just long enough for us to learn something new. When a gamma-ray burst erupts, it doesn't blast energy in all directions like a firework. Instead, it channels its fury into narrow, ultra-focused jets, cosmic blowtorches piercing through space. But here's the catch. We can't see how tight those jets are just from the initial flash. That's where the afterglow comes in. As the jet plows into surrounding gas, it creates a glowing aftermath that fades slowly until it doesn't. Suddenly, the afterglow's brightness takes a sharp nosedive. This isn't a glitch, it's the jet break. What's happening? The jet, initially too narrow for us to notice its edges, has finally spread out enough that we can see its side. It's like watching a spotlight beam widen until you spot its rim. That sudden drop tells astronomers the jet's exact angle, how tightly focused it was. And that's a game changer. Why? Because once we know the jet's width, we can calculate the true energy of the explosion. Without this, we'd underestimate GRB power by hundreds or even thousands of times. Imagine judging a laser's strength while only seeing a pinprick of its light. That's the challenge jet breaks solve. They're the universe's way of handing us a measuring tape for its most violent outbursts. So next time you hear about a gamma-ray burst's afterglow flickering, remember, that tiny dip in brightness is a cosmic clue, helping us measure the unimaginable forces shaping the early universe. Now, let's unravel one of the most compelling cosmic partnerships, the bond between long gamma-ray bursts and supernova. Picture this: a massive star, having burned through its fuel, collapses under its own weight. But instead of fading quietly, it goes out with a spectacular bang, triggering both a supernova and a gamma-ray burst in one explosive act. This isn't just theoretical. Take GRB 030329, detected in 2003. Weeks after its initial flash, astronomers spotted something extraordinary, a supernova dubbed SN 2003DH. Its light curve and chemical fingerprints matched a Type I supernova, a rare breed born from stars that have shed their outer hydrogen and helium layers before exploding. Here's why this duo matters. Type I supernova come from fast-spinning, massive stars, the same kind thought to power long GRBs. When we see a distant GRB paired with one of these supernova, it's like finding a cosmic signature, proof that the burst wasn't just a random flare, but the death cry of a colossal star. And the implications are huge. GRB 030329 wasn't alone. Over the years, multiple long bursts have shown this supernova connection, cementing the idea that these events are two sides of the same cataclysmic coin. It's a reminder that even in the farthest reaches of the universe, the rules of stellar life and death hold true, violent, predictable, and endlessly fascinating. So next time you hear about a gamma-ray burst lighting up the cosmos, remember, there's a good chance a supernova's fiery farewell is hiding in its afterglow, waiting to tell its story. But here's where the cosmic plot thickens. Not every long gamma-ray burst follows the script. Take GRB 060614, a burst that defied expectations. When astronomers trained their telescopes on its aftermath, they found something startling, or rather, the absence of something. There was no supernova. No fiery stellar farewell, just silence where there should have been an explosion. This wasn't a case of missing the show. Teams scoured the data for weeks, using some of the most powerful observatories on Earth and in space. Yet nothing. GRB 060614's host galaxy lay a mere 1.6 billion light-years away, close enough that even a faint supernova would have been visible. Its absence sent shockwaves through the astrophysics community, forcing a rethink of how these bursts form. So what's the alternative? One leading theory points to binary mergers, two compact objects like neutron stars spiraling together. These collisions typically produce short GRBs, but GRB 060614 lasted nearly 2 minutes, blurring the line between burst types. Could some long GRBs actually be mergers in disguise? Or is there another, even stranger engine powering these cosmic outliers? The mystery doesn't end there. Other bursts like GRB 050724 and GRB 070614 also lack supernova signatures. Together, they hint at a hidden diversity in GRB origins, a reminder that the universe loves to surprise us. For every rule we uncover, there's an exception waiting to rewrite the textbooks. And that's the thrill of gamma-ray bursts. Just when we think we've cracked their code, they throw us a curveball, pushing us to dig deeper into the cosmos' most explosive secrets. Now, let's step into the eerie realm of the universe's ghostly outliers, ultra-long gamma-ray bursts. These enigmatic events don't just flicker out in seconds or minutes. They linger, stretching their emission for hours, even defying our usual categories. Take GRB 111209A, a burst that refused to fade, shining brightly for nearly 7 hours. That's not just unusual, it's practically unheard of in the GRB playbook. So what fuels these marathon explosions? One compelling theory points to the collapse of blue supergiants, massive stars dozens of times heavier than our Sun. Unlike their shorter-lived cousins, these stars have extended outer layers, which could slow down the collapse process, stretching the burst into an hours-long spectacle. Imagine a cosmic slow-motion detonation, where the star's death throes unfold at a glacial pace by GRB standards. But there's another, even more dramatic possibility titled disruption events. Picture a star wandering too close to a supermassive black hole, torn apart by gravitational forces in a cataclysmic shredding. While these events usually produce flares in other wavelengths, some theorists suggest they could also spawn ultra-long GRBs under the right conditions. It's a cosmic tug-of-war where the black hole's appetite creates a light show lasting hours. What makes these ghostly bursts so fascinating isn't just their duration, it's what they reveal about the diversity of stellar deaths. Every outlier, every rule breaker like GRB 111209A, forces us to expand our understanding of how stars live and die. And in that expansion, we uncover new chapters in the story of the universe itself, one long, luminous mystery at a time. Now, let's turn our attention to another cosmic clue hidden in the aftermath of gamma-ray bursts, the mysterious infrared flares known as dust echoes. These aren't your typical afterglows. Instead of fading steadily, some GRBs produce a second act, a delayed infrared flare that can appear days or even weeks after the initial burst. It's like the universe hitting the replay button, but this time in a different wavelength. So what's causing this encore? The leading explanation points to vast clouds of cosmic dust surrounding the burst. When the gamma ray blast slams into these dust particles, it heats them up, causing them to re-emit the energy as infrared light. But here's the twist: because the dust is spread out at varying distances from the burst, the light takes longer to reach us from the more distant regions, creating that delayed flare. Imagine tossing a pebble into a pond and watching the ripples bounce off rocks at different distances. Each echo tells you something new about the pond's hidden structure. These dust echoes aren't just cosmic curiosities, they're treasure maps. By studying them, astronomers can piece together the distribution and composition of dust in the early universe. This is crucial because dust plays a starring role in the life cycle of galaxies, shielding young stars, fostering molecule formation, and even hiding entire regions of star birth from our telescopes. Every infrared flare is like a fingerprint, revealing the invisible scaffolding of the cosmos. What makes this phenomenon so thrilling is its potential to solve a long-standing puzzle: how and when dust first appeared in the universe. Some of the most distant GRBs show surprisingly strong dust echoes, suggesting that dust was already plentiful even when the universe was in its infancy. That challenges our models of how quickly heavy elements, the building blocks of dust, could have spread through space. With each new dust echo detected, we're not just watching a burst's aftermath, we're uncovering the recipe for the universe's cosmic kitchens. Here's the next section of the script, seamlessly continuing from the previous content while introducing Fact 21 in an engaging way. Now, let's tackle a cosmic head-scratcher, the so-called luminosity crisis. Early astronomers were baffled when their models predicted far more distant gamma-ray bursts than they actually observed. It was like expecting a packed concert but only finding a handful of attendees. The math just didn't add up. The breakthrough came when researchers realized they'd overlooked a critical detail. The stars behind these bursts aren't just any stars. Long-duration GRBs, the kind that dominate the distant universe, have a strong preference for low metallicity environments. In other words, they're picky about their birthplace. These explosions thrive in galaxies with fewer heavy elements, places where stars are built from mostly hydrogen and helium, the universe's original building blocks. Why does this matter? Because metal-poor stars behave differently. They lose less mass through stellar winds, allowing them to retain the angular momentum needed to produce the ultra-fast spinning cores that power GRBs. Revised models now factor in this metallicity bias, and suddenly the numbers make sense. The early universe, with its abundance of pristine, metal-poor galaxies, was a GRB factory, but only under the right conditions. This adjustment didn't just solve a mystery, it reshaped our understanding of cosmic evolution. By studying GRB rates, we're essentially taking a census of star-forming environments across time, revealing how the universe's chemical makeup has changed. Every distant burst is a clue, helping us piece together why some corners of the cosmos light up with these spectacular explosions while others stay dark. Now, let's turn our attention to an explosive partnership that redefines cosmic powerhouses: the fascinating link between gamma-ray bursts and superluminous supernova. Picture this: a star doesn't just die, it unleashes a supernova so bright it outshines entire galaxies, and in some cases, it teams up with a gamma-ray burst for the ultimate cosmic double feature. Take the case of supernova 2011 KL and its partner in crime, gamma-ray burst 111209A. When astronomers spotted this duo, they realized they were witnessing something extraordinary. The supernova wasn't just bright, it was hundreds of times more luminous than a typical stellar explosion, and the gamma-ray burst that accompanied it was equally intense. So what's fueling these extreme events? The leading theory points to magnetar neutron stars with magnetic fields so strong they could wipe a credit card clean from halfway across the galaxy. When a massive star collapses, it can leave behind one of these spinning powerhouses. As the magnetar's immense magnetic field interacts with the surrounding debris, it pumps energy into the explosion, turning an already spectacular supernova into a superluminous one. This connection isn't just a cosmic curiosity, it's a clue. By studying these paired events, astronomers are piecing together how the most energetic explosions in the universe are born. It's a reminder that sometimes the universe's most dazzling shows come from the strangest collaborations, and with every new discovery, we're learning just how creative cosmic destruction can be. Now, let's peel back the curtain on one of gamma-ray bursts' best-kept secrets, the so-called choked jet scenario. Imagine a star collapsing in on itself, ready to unleash a devastating gamma-ray burst, but something goes wrong. The jet of energy, which would normally blast its way out into space at nearly the speed of light, gets trapped inside the dying star. Instead of a brilliant flash visible across the cosmos, the burst fizzles out, leaving behind little to no trace for telescopes to detect. This isn't just a cosmic fluke, it's a whole hidden population of gamma-ray bursts that astronomers suspect might be lurking in the shadows. Think of it like a firework that never makes it out of its shell. The explosion happens, but it's muffled, invisible to us. That's why some of the most violent stellar deaths might be slipping under our radar entirely. So how do we even know these choked jets exist? Clues come from supernovae that seem unusually energetic but lack the telltale gamma-ray burst we'd expect. Some researchers believe these could be the smoking guns of failed jets, events where the star's core tried to produce a gamma-ray burst but couldn't punch through its own outer layers. The implications are huge. If choked jets are common, it means we've been missing a significant piece of the puzzle when it comes to understanding how massive stars die. It's a humbling reminder that even the universe's most violent explosions don't always go as planned, and that some of its biggest mysteries might be hiding in plain sight just beyond our view. But here's something even more puzzling. What if we could find gamma-ray bursts without actually seeing the gamma rays? That's the bizarre reality behind orphan afterglows. Picture this: a gamma-ray burst fires off its jet, but it's not pointed directly at Earth. We miss the initial blast of gamma rays entirely. Yet, as that jet plows through space, it heats up surrounding gas, creating a faint afterglow that lingers in visible light, X-rays, or radio waves. Astronomers are now hunting these orphans like cosmic detectives, scanning the skies for afterglows without apparent burst. It's a bit like finding footprints without ever seeing the animal that made them. These elusive signals could be key to uncovering gamma-ray bursts we'd otherwise miss, especially those with jets angled away from us. Why does this matter? Because every orphan afterglow we find helps complete the true census of gamma-ray bursts in the universe. Right now, our records are biased toward bursts that happen to point their jets in our direction. But by catching these sideways events, we get a fuller picture of how often stars die in these catastrophic explosions, and how much energy they're really pumping into the cosmos. The hunt isn't easy. Orphan afterglows are faint, fleeting, and often buried in a sea of other cosmic signals. But with next-generation telescopes sharpening their focus, we're inching closer to spotting more of these hidden giants. And each discovery reminds us, sometimes the universe's biggest fireworks show is happening just out of view. Now, let's shift our gaze to a different kind of cosmic spectacle, one where gamma-ray bursts aren't just about massive stars collapsing, but about neutron stars crashing together in a violent embrace. When two neutron stars collide, they don't just create a short gamma-ray burst. They also unleash something far more exotic, a macronova or kilonova. Picture this: as the neutron stars merge, they spew out a cloud of ultra-dense material packed with neutrons. In this chaotic environment, atoms can't form normally. Instead, they undergo something called the R process, a rapid capture of neutrons that forges heavy elements like gold, platinum, and uranium. But here's the catch: these freshly minted elements are unstable. They decay almost immediately, heating up the surrounding debris and producing a thermal glow that lingers in the infrared for days or even weeks. This is how we spotted the aftermath of GW 170,817, the first neutron-star merger ever detected with both gravitational waves and light. Its macronova signature was unmistakable, a faint but persistent infrared glow that confirmed theorists' predictions, and it wasn't just a light show. That single event produced an estimated Earth's mass worth of gold, proving that these collisions are cosmic factories for the universe's heaviest elements. What makes macronovae so special for distant gamma-ray bursts? Because they're a dead giveaway. Even if a neutron star merger's gamma-ray jet isn't pointed at us, the macronova's infrared glow is visible from almost any angle. That means we could potentially find mergers in the early universe that would otherwise be invisible, filling in gaps in our understanding of how often these events occur and how they shaped the chemical makeup of the cosmos. The hunt is on, with telescopes like the James Webb Space Telescope peering deeper into the infrared. We're on the verge of uncovering more of these hidden mergers. And each one could rewrite the story of how the universe went from a sea of simple hydrogen to the rich, element-filled cosmos we see today. Now, here's something that might surprise you. When we map out the history of star formation across the universe, we see a clear peak around redshifts of 2 to 3, a time when galaxies were churning out new stars at an incredible rate. But gamma-ray bursts, they don't follow that trend. Instead, they show up even farther back in time at higher redshifts where star formation was supposedly less intense. So what's going on? The answer lies in the kind of stars that produce GRBs. These aren't your average run-of-the-mill stars. Long-duration gamma-ray bursts come from massive, fast-burning stars, the kind that thrive in environments with very few heavy elements, what astronomers call low metallicity conditions. And here's the twist: in the early universe, galaxies were much more likely to be metal-poor. That means GRB progenitors were far more common back then, even if the overall star formation rate wasn't at its peak. This low metallicity bias skews the GRB record, making them appear more frequently in the distant universe than you'd expect based on star formation alone. It's like searching for a rare type of tree in a forest. If that tree only grows in specific soil, you'll find it in places where that soil exists, not necessarily where the most trees are growing. This mismatch teaches us something profound. GRBs aren't just tracing star formation, they're highlighting the unique conditions that give rise to the universe's most extreme stellar explosions. And that makes them invaluable tools for piecing together the cosmic puzzle of how galaxies evolved, not just in numbers but in chemistry too. Now, let's spin into another fascinating piece of the gamma-ray burst puzzle, literally. The stars that produce these colossal explosions don't just need to be massive and metal-poor, they also have to be spinning incredibly fast. Think of it like an Olympic figure skater pulling their arms in to accelerate, except here, the skater is a dying star, and the spin is so intense it helps launch a jet of material at nearly the speed of light. This rapid rotation isn't just a minor detail, it's a make-or-break factor for GRBs. When a massive star collapses, its spin acts like a power source, winding up magnetic fields and funneling energy into those narrow, ultra-relativistic jets we detect as gamma-ray bursts. Without that dizzying spin, the star might just fizzle out as an ordinary supernova, leaving no GRB behind. And here's where distant gamma-ray bursts drop a major clue. The fact that we see so many of them in the early universe suggests something extraordinary. Back then, massive stars weren't just metal-poor, they were also spinning much faster than their modern counterparts. Why? One leading theory points to the environment. In the primordial universe, stars likely formed in denser, more turbulent gas clouds with fewer heavy elements to slow them down. Less metal means less stellar wind, which means less angular momentum gets sapped away over time. The result, stars that keep their spin and pack the punch needed to produce GRBs. So every time we detect a gamma ray burst from the cosmic dawn, we're not just seeing a flash of light. We're glimpsing the ghost of a star that spun like a top, a relic of an era when the universe's most violent explosions were far more common. It's a reminder that the rules of stellar physics weren't just different back then, they were dialed up to 11. Now let's venture even further back in time, to the very first generation of stars. These weren't just any stars, they were the universe's pioneers, known as population 3 stars. Unlike the stars we see today, these ancient giants were made purely of hydrogen and helium, forged from the raw ingredients of the Big Bang itself. No heavy metals, no pollution, just pristine cosmic fuel. And here's where things get speculative but thrilling. Some astronomers think the most distant gamma ray bursts we detect might be the final cries of these population 3 stars. Imagine a star so massive and pure that its death unleashes an explosion unlike anything in the modern universe. No metals mean weaker stellar winds, allowing these stars to retain more mass and spin even faster, perfect conditions for a GRB on steroids. But why haven't we confirmed one yet? Population 3 stars lived fast and died young, vanishing billions of years ago. Their GRBs would be incredibly rare and faint by the time their light reaches us. Plus, their unique fingerprints, like the absence of certain metal signatures in their afterglows, are devilishly hard to spot across such vast cosmic distances. Yet the hunt continues. If we could find a GRB tied to a population 3 star, it would be like uncovering the fossil of the universe's first predator. Not just a glimpse into the era of the first stars, but a direct window into how they shaped the cosmos we know today. Until then, these metal-free titans remain one of gamma-ray astronomy's most tantalizing what-ifs. Now, let's shift our gaze to one of the most mysterious possibilities in gamma-ray burst research: the potential link between these cosmic explosions and dark matter. While we've explored how GRBs are tied to stars and stellar deaths, some scientists have wondered if dark matter, the invisible glue holding galaxies together, could also play a role. The idea goes like this: if dark matter particles decay or collide, they might release bursts of energy, possibly even gamma rays. In theory, this could mimic the signals we see from traditional GRBs. Imagine uncovering a GRB that wasn't from a dying star at all, but from the annihilation of dark matter in the depths of space. It's a tantalizing thought, offering a whole new way to study this elusive substance that makes up most of the universe's mass. But here's the catch so far: there's zero concrete evidence linking distant gamma-ray bursts to dark matter. Every GRB we've traced back to its origins has pointed to astrophysical sources like collapsing stars or merging neutron stars. The energy signatures, the afterglows, even the host galaxies all align with these known processes, leaving little room for dark matter explanations. That doesn't mean the idea is dead, though. Some researchers keep searching for unusual GRBs that defy conventional explanations, hoping to spot a dark matter fingerprint. Until then, the connection remains a fascinating what-if, blending two of cosmology's biggest puzzles into one high-stakes mystery. Up next, we'll dive into how polarized light from GRB afterglows reveals hidden details about magnetic fields and jet structures, another tool in our quest to decode these cosmic fireworks. Now, let's turn our attention to a powerful tool in gamma-ray burst research: the secrets hidden in polarized light. When a GRB's afterglow emits polarized light, it's like the universe handing us a decoder ring. This subtle property of light, where its waves vibrate in a preferred direction, carries clues about the magnetic fields tangled within the burst, the shape of its high-speed jets, and even the environment surrounding the explosion. Think of it like sunlight reflecting off a lake. If the water is calm, the light scatters randomly, but if the surface is disturbed, the reflections align in certain directions, revealing the water's movement. Similarly, polarized afterglow light tells us how magnetic fields are woven through the GRB's jet, or how the jet itself might be warped or uneven. For example, if the polarization changes over time, it could mean the jet is wobbling or that we're seeing it from an off angle, adding a new layer to our understanding of these violent events. One of the most exciting revelations from this technique is how it exposes the invisible scaffolding of magnetic fields in deep space. Some distant GRBs show highly polarized afterglows, hinting at ultra-strong, organized magnetic fields in their host galaxies, a detail almost impossible to detect otherwise. Others display chaotic polarization patterns, suggesting turbulent environments where the burst plowed through dense clouds of gas and dust. While polarized light doesn't solve every GRB mystery, it's a game-changer for piecing together their anatomy. Next, we'll explore why short gamma-ray bursts seem to avoid the early universe and what that tells us about cosmic evolution. Now, here's something curious about gamma-ray bursts that might surprise you. While we've been focusing on the long, dramatic bursts from the early universe, there's another type that's conspicuously missing from the cosmic record: short hard bursts, or SHB. These quick, intense flashes, often lasting less than 2 seconds, are the cosmic signatures of neutron stars colliding or black holes merging. But here's the twist: when we look deep into the distant universe, these SHBs practically vanish. Why does this matter? Well, their absence tells a fascinating story about the early cosmos. Since SHBs are linked to neutron star mergers, their scarcity at high redshifts, meaning far back in time, suggests these dense stellar remnants weren't pairing up as often back then. It's like digging through ancient ruins and finding no evidence of certain tools. You start to realize those tools might not have existed yet or were incredibly rare. One theory is that neutron stars needed more time to form, find partners, and eventually spiral into each other. In the early universe, massive stars were exploding as supernovae, but the resulting neutron stars might have been too young, too scattered, or simply not in binary systems yet. Another possibility: the environments back then, like lower metal content in stars, could have made it harder for these mergers to happen. This distinction between long GRBs and SHBs isn't just academic. It's a clue about how the universe evolved. Long bursts dominate the early cosmic scene because massive stars lived fast and died young, while the slower, more patient dance of neutron star mergers took billions of years to become common. Next, we'll revisit a landmark burst that shattered expectations about what GRBs could reveal: the groundbreaking GRB 050904. Now, let's turn our attention to a burst that rewrote the rules: GRB 050904. Detected in 2005, this wasn't just another gamma-ray flash. With a redshift of 6.3, it became the first GRB ever observed from the cosmic dawn, a time when the universe was just 900 million years old. That places it squarely in the epoch of reionization, when the first stars and galaxies were tearing apart the fog of hydrogen that filled the early cosmos. What made GRB 050904 so groundbreaking? For starters, its sheer distance. Before this, astronomers weren't sure if gamma-ray bursts could even be detected that far back in time. But here was a burst so bright, it pierced through 13 billion years of cosmic history, landing squarely in our telescopes. Its afterglow, studied by observatories like Subaru and Gemini, revealed something extraordinary: the fingerprints of primordial gas. By analyzing how its light interacted with hydrogen clouds along the way, scientists got a direct look at the universe's transition from opaque to transparent. But GRB 050904 didn't just break distance records. It also challenged assumptions about the early universe. Its energy output was staggering, rivaling even nearby bursts, which suggested that the mechanisms powering GRBs were already in full swing less than a billion years after the Big Bang. And its host galaxy, faint and small, a far cry from the massive galaxies we see today. This hinted that even in these modest cosmic neighborhoods, conditions were ripe for the birth and explosive death of massive stars. In many ways, GRB 050904 was a proof of concept. It showed that gamma-ray bursts could serve as lighthouses, illuminating the darkest corners of the early universe. And with that, the race was on to find even more distant bursts, a quest that would soon take us closer than ever to the dawn of time itself. Next, we'll explore the unsung heroes of GRB detection, the robotic telescopes that made these discoveries possible. Now, let's shine a light on the unsung heroes behind these cosmic discoveries, the robotic telescopes that changed the game. Before advanced satellites like SWIFT dominated the scene, ground-based pioneers like LOTES and ROTSI were already racing against time to catch GRB afterglows. These weren't your typical observatories. They were sleek, automated systems designed to react in seconds, not hours. Take ROTSI III, for example. This nimble telescope, stationed in Texas, had one job: to swing into action the moment a gamma-ray burst alert came in. No human intervention needed. In the late 1990s, it proved its worth by capturing the optical afterglow of GRB 990123, a milestone that showed robotic telescopes could keep up with the universe's fastest explosions. But why does speed matter? Gamma-ray burst afterglows fade fast, sometimes in minutes. Traditional telescopes, bogged down by manual adjustments, often missed the show. ROTSI and its peers changed that. Their rapid slewing and automated tracking meant they could lock onto a burst's location almost instantly, giving astronomers their first real-time glimpses of these fleeting cosmic fireworks. LOTES, short for Livermore Optical Transient Imaging System, was another trailblazer. Though less famous, it played a crucial role in testing the waters for rapid follow-up observations. Together, these early systems laid the groundwork for today's global networks of robotic telescopes, which now work in tandem with satellites to chase GRBs across the sky. What's truly remarkable is how these humble beginnings shaped modern astronomy. Without ROTSI and LOTES proving that rapid response was possible, we might never have developed the tools to study distant bursts like GRB 050904 in such detail. They turned GRB hunting from a lucky accident into a precise science, one that continues to push the boundaries of what we know about the early universe. Next, we'll unravel another GRB mystery: the puzzling delays between some bursts and their accompanying supernova. Now, here's something that'll make you scratch your head. Why do some gamma-ray bursts and their supernova companions show up to the cosmic party at different times? Picture this: a massive star collapses, triggering a GRB, but the supernova explosion that follows doesn't happen right away. Instead, there's a gap, sometimes hours, even days. What's causing this delay? One leading theory points to the jets themselves. When a star collapses, it doesn't just explode uniformly. Narrow, ultra-fast jets punch through the star's outer layers, creating the GRB we detect. But those jets take time to tunnel their way out. Meanwhile, the rest of the star is still collapsing inward, building up energy until boom, the supernova erupts. Think of it like lighting a fuse. The GRB is the spark, but the supernova is the full blast, and the delay depends on how long that fuse takes to burn. Then there's the star's structure. Not all massive stars are built the same. Some have dense, turbulent outer layers that slow down the jets, while others might have magnetic fields that twist and redirect energy, delaying the supernova's debut. GRB 060218, for example, had a bizarre week-long gap between its weak gamma-ray emission and its unusual supernova, SN 2006 AG. Cases like this force astronomers to rethink how stars die and how much variety exists in their final moments. But here's the kicker, these delays aren't just quirks. They're clues. By studying the gaps between GRBs and their supernova, scientists can piece together the hidden physics of stellar collapse, how energy travels through a dying star, how jets interact with their surroundings, and even how elements get forged in the chaos. Every delayed supernova is like a cosmic stopwatch ticking away until it reveals another piece of the puzzle. Up next, we'll tackle another enigma, the mysterious GRBs that seem to come from nowhere with no host galaxy in sight. Now let's turn our attention to one of the strangest puzzles in gamma-ray burst astronomy, the ones that seem to come from empty space. Most GRBs have a home, a host galaxy we can point to, but a handful of them defy expectations. When astronomers train their telescopes on the spot where the burst occurred, they find nothing. No galaxy, no star cluster, just darkness. So where did these ghostly bursts come from? One possibility is that these hostless GRBs originate in galaxies too faint for our current telescopes to detect. Imagine a tiny, dim dwarf galaxy, billions of light years away, barely holding on to a few stars. It might be so faint that even Hubble struggles to spot it. Yet inside that galaxy, a massive star could still collapse, producing a GRB bright enough for us to see across the universe. The burst outshines its home by a staggering margin, leaving us with a cosmic mystery. Then there's the wilder idea, what if some GRBs don't come from galaxies at all? In the early universe, massive stars might have formed in the vast, empty stretches between galaxies, in regions where gas clouds drifted alone. These isolated stars would live fast, die young, and leave behind GRBs with no galactic address. It's a radical thought, but if true, it would mean the universe's first stars didn't just light up galaxies, they also flickered in the void. Of course, there's always the chance we're missing something. Maybe the host galaxy is hiding behind dust, or perhaps the GRB was flung out of its home by a gravitational kick. Every time we find one of these orphan bursts, it forces us to question what we know about where and how GRBs form. And with next-generation telescopes like JWST peering deeper than ever, we might finally solve the riddle of the hostless GRBs or uncover even stranger truths. Coming up, we'll explore another twist in the GRB saga, the rare but fascinating cases where these bursts appear to overlap with the violent hearts of active galaxies. Now let's venture into one of the most intriguing debates in modern astrophysics, the possible connection between gamma-ray bursts and another cosmic mystery, fast radio bursts. Fast radio bursts, or FRB, are fleeting blasts of radio waves that last just milliseconds, yet pack enough energy to rival an entire day's output from our Sun. At first glance, they seem worlds apart from GRBs, which unleash their fury in gamma rays over seconds or minutes. But could these two phenomena be distant cousins or even different faces of the same cosmic beast? Some theorists suggest that certain types of GRBs, particularly the short-duration ones born from neutron star collisions, might share a common engine with FRBs. Picture this: when two neutron stars spiral together and merge, they could produce not just a GRB, but also a jet of charged particles whipping through magnetic fields at nearly light speed. Under the right conditions, that jet might generate both gamma rays and a fleeting radio burst. It's a tantalizing idea, one that would link two of the universe's most explosive events. But here's the catch. While a handful of FRBs have been tentatively linked to known astrophysical sources, none have been definitively tied to distant GRBs. The most famous example, FRB 2020-024, erupted from a magnetar in our own galaxy, a far cry from the high-energy chaos of a cosmic gamma-ray burst. And when astronomers scour the skies for FRBs coinciding with distant GRBs, they come up empty-handed. The silence is deafening. That hasn't stopped the speculation, though. Some models propose that FRBs could be the echoes of GRB jets interacting with surrounding material, or even signals from newly formed magnetars. the same exotic stars thought to power some long GRBs. Others argue that the two phenomena are entirely separate, with FRBs arising from entirely different processes, like flaring magnetars or evaporating black holes. For now, the debate remains wide open, a reminder of how much we still don't understand about the universe's most violent outbursts. What's clear is that every new FRB and GRB detection brings us closer to an answer. With radio telescopes like CHIME and gamma-ray observatories like Fermi working in tandem, we might one day catch these cosmic fireworks in the act, revealing whether they're strangers, acquaintances, or something far more intimate. Up next, we'll examine a GRB that defied expectations, challenging our models with a photon so energetic it seemed impossible. Now let's turn our attention to a gamma-ray burst that flipped the script on what we thought was possible. GRB 130427 wasn't just another burst, it was a cosmic rebel that broke the rules. Located relatively close by at a redshift of 0.34, this event should have been predictable. But when it unleashed a photon with a staggering 95 gigaelectronvolts of energy, scientists were left scratching their heads. Here's why this was such a shock. High-energy photons like this are supposed to get absorbed or scattered as they travel through space, especially over long distances. Yet this monster of a photon arrived intact, defying expectations. It forced researchers to reconsider how gamma-ray bursts produce such extreme energies, suggesting that the mechanisms at work might be universal, not just limited to the distant early universe. What makes GRB 130427 even more fascinating is how it bridges the gap between nearby and distant bursts. Most ultra-high-energy photons come from GRBs billions of light-years away, where the universe's expansion stretches their light. But this one was practically in our backyard, cosmically speaking. That means whatever process cooked up that 95 GeV photon isn't just a quirk of the ancient cosmos, it's happening right now, in galaxies not so different from our own. The implications ripple far beyond this single event. If nearby GRBs can produce photons this energetic, it challenges long-held assumptions about particle acceleration and magnetic fields in these explosions. Some theories suggest that shocks within the jet or interactions with surrounding material could be the key. Others speculate that we're seeing the fingerprints of an even more exotic process, one that we've yet to fully understand. One thing's for sure, GRB 130427 proved that the universe still has surprises up its sleeve, and as detectors grow more sensitive, we may find that what we once called anomalies are just the tip of the cosmic iceberg. Up next, we'll dive into another head-scratcher, a gamma-ray burst that seemed to defy the very laws of physics, if only for a fleeting moment. Now let's shift gears to a scenario that sounds like something straight out of a sci-fi blockbuster: supermassive neutron stars acting as cosmic powerhouses for short gamma-ray bursts. Picture this, a neutron star so dense and spinning so fast that it defies gravity's pull, staving off collapse just long enough to unleash a burst of energy that lights up the universe. This is the heart of the supermassive neutron star, or SMNS, model. Unlike typical neutron stars that collapse into black holes almost instantly after formation, these rare beasts buy themselves extra time, sometimes minutes or even hours, thanks to their breakneck rotation. That spin generates centrifugal force, essentially pushing back against gravity's crush. During this brief window, the star can channel its energy into a jet, potentially producing a short gamma-ray burst before it finally succumbs and becomes a black hole. What makes this idea so compelling is how it solves a puzzle about certain short GRBs. Some of these bursts have features that don't quite fit the classic neutron star merger explanation. For example, occasional extended emission or X-ray flares might point to a central engine that's still active, like a spinning SMNS dumping energy into its surroundings. It's like hearing an engine revving long after the car's ignition was turned off. Something unexpected is keeping the show running. the SMNS scenario also opens up wild possibilities for gravitational wave astronomy. If these stars exist, their final collapse should send ripples through spacetime, offering detectors like LIGO and Virgo a chance to catch the crescendo of their existence. Pair that with a gamma-ray burst, and you've got a cosmic multi-messenger event that could rewrite textbooks. Of course, the SMNS model isn't without its skeptics. Some argue that the conditions needed to form these stars, just the right mass, just the right spin, might be too rare to explain more than a handful of observed bursts. Others suggest alternative explanations, like accretion disks around newborn black holes could produce similar signals. But that's the beauty of gamma-ray bursts. They keep theorists on their toes, forcing us to imagine ever more exotic physics. One thing's clear: whether SMNSs are real or not, they've given us a thrilling new lens to explore the extremes of stellar death. And as our telescopes and detectors grow sharper, we might just catch one of these spinning titans in the act. Up next, we'll unravel the mystery of a gamma-ray burst so bright it was briefly visible to the naked eye, a true cosmic fluke that still baffles astronomers today. Now let's talk about a gamma-ray burst so extraordinary it briefly outshone the entire night sky, a cosmic stroke of luck that still leaves astronomers in awe. Meet JRBs 080319b, a burst so bright it was momentarily visible to the naked eye from Earth despite being nearly 7.5 billion light-years away. This freak event unfolded in March 2008 when satellites detected a gamma-ray burst unlike any other. What made it unique? A perfect alignment of its ultra-relativistic jet aimed directly at Earth like a cosmic spotlight. Most GRB jets are narrow, and if they're even slightly off-axis, we only catch a fraction of their light. But this one hit the bullseye, amplifying its brightness to staggering levels. For about 30 seconds, its optical flash reached magnitude 5.3, bright enough to see from a dark location without telescopes. The odds of this happening: roughly 1 in 10,000. It's like winning the cosmic lottery. The burst's afterglow also broke records, remaining detectable for weeks and providing a treasure trove of data. Astronomers realized the jet's core was surrounded by a wider, less energetic component, which helped sustain the afterglow long after the initial flash faded. But here's the twist: JRB 080319b wasn't just a fluke. It taught us that even distant bursts can temporarily outshine their host galaxies if conditions are just right. It also raised questions about how many similar events we might have missed because their jets weren't pointed at us. This burst remains a benchmark for extreme cosmic phenomena, proving that sometimes the universe hands us a front-row seat to its most dazzling shows. Up next, we'll examine an even more recent monster, JRB 221009a, a burst so powerful it temporarily blinded our detectors and rewrote the rules on JRB energy limits. Shifting our gaze to a more recent cosmic spectacle, let's unpack the sheer ferocity of JRB 221009a, a burst so intense it pushed our detectors to their limits. Detected in October 2022, this monster unleashed energy on a scale that defied expectations, even for gamma-ray bursts. What set this event apart wasn't just its brightness, it was the way it saturated instruments across multiple observatories, as if the universe had cranked the volume to 11. With a redshift of 0.151, it wasn't the most distant GRB ever seen, but its proximity allowed scientists to measure its energy with unprecedented precision. The numbers were staggering. In just a few minutes, it released more energy than our Sun will over its entire 10 billion-year lifespan. But here's the real kicker. JRB 221009 wasn't just a record breaker, it was a rule changer. Its energy profile forced astronomers to revisit models of how GRBs operate, particularly the mechanisms that accelerate particles to near light speeds. Some theories suggest magnetic fields in the jet played an outsized role, while others point to shock waves within the collapsing star itself. This burst also offered a rare opportunity to study the interstellar medium in fine detail. As its light traveled toward Earth, it illuminated dust clouds in our own galaxy, creating faint echoes that helped map Milky Way structures we'd never seen so clearly. Perhaps most importantly, GRB 221009 proved that even nearby bursts can teach us about their distant cousins. If a relatively close event could pack this much power, imagine what the early universe's GRBs, born from faster spinning, metal-poor stars, might have been capable of. It's a humbling reminder that the cosmos still holds surprises, and sometimes they arrive brighter than we ever thought possible. Now let's turn our attention to one of the rarest and most puzzling overlaps in cosmic phenomena: gamma-ray bursts occurring near active galactic nuclei. These supermassive black hole-powered engines, known as AGN, are already some of the most energetic objects in the universe. But when a GRB erupts in their vicinity, it creates a celestial puzzle that challenges our understanding of stellar deaths and galactic environments. Take GRB 101225A, for example. Detected on Christmas Day in 2010, this burst stood out because of its unusual location close to the heart of a galaxy hosting an active nucleus. Normally, GRBs originate in star-forming regions far from galactic centers, where massive stars live and die. But here, the burst's proximity to the AGN raised eyebrows. Could the violent processes around a supermassive black hole, like swirling accretion disks or powerful jets, somehow trigger or influence a GRB? Scientists have floated intriguing theories. One suggests that AGN-driven instabilities might disrupt the normal life cycles of massive stars, either by intensifying their rotation or by stripping away their outer layers prematurely. Another idea proposes that the extreme gravitational tides near an AGN could compress gas clouds, sparking rapid star formation, and eventually the birth of stars destined to become GRBs. What makes these cases so valuable is their rarity. Out of thousands of observed gamma-ray bursts, only a handful show this AGN connection. Each one offers a unique laboratory to study how the most extreme environments in galaxies might shape the deaths of their most massive stars. And while the link isn't yet fully understood, these overlaps remind us that the universe loves breaking its own rules, and that sometimes the most fascinating discoveries come from the places we least expect. Up next, we'll explore how gamma-ray bursts might even leave their mark on the oldest light in the cosmos, the cosmic microwave background. Now, let's venture into one of the most mind-bending ideas in gamma-ray burst research: the possibility that these cosmic explosions might leave faint fingerprints on the oldest light in the universe. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint whisper of radiation that fills every corner of space. But what if the photons from distant GRBs could interact with this ancient light, creating subtle ripples or secondary signals we might detect? Imagine a gamma-ray photon racing across the universe for billions of years, only to collide with a particle of CMB light along the way. This interaction could scatter the photon, altering its energy or direction. Scientists speculate that these scattered photons might form a faint, diffuse glow, a kind of echo of the original GRB hidden within the CMB itself. Detecting such signals would be like finding cosmic breadcrumbs, hinting at GRBs so distant or faint that their direct light never reached us. The challenge, of course, is separating these hypothetical signals from the CMB's natural fluctuations. The cosmic microwave background is already a tapestry of tiny temperature variations, remnants of the universe's infancy. But advanced telescopes and future missions, like those studying the CMB with unprecedented precision, might one day spot these elusive GRB imprints. If they do, it would open a new window into the earliest epochs of star formation and the violent deaths of the universe's first massive stars. This idea pushes the boundaries of what we thought possible, blending the study of the universe's most energetic explosions with its oldest light. And while the evidence is still theoretical, it's a thrilling reminder that even the faintest whispers of the cosmos might hold secrets waiting to be uncovered. Up next, we'll examine a GRB that defied all expectations, lasting not seconds or minutes but an entire week. Now, let's turn our attention to a gamma-ray burst that left astronomers scratching their heads. GRB 060218. This burst was a true oddity, breaking several rules scientists thought they understood about these cosmic explosions. Located relatively close at a redshift of 0.033, it was one of the nearest GRBs ever detected, yet its behavior was anything but typical. Most gamma-ray bursts last mere seconds or minutes, but GRB 060218 stretched on for an entire week, emitting faint but persistent gamma rays. Even stranger, it was accompanied by a supernova, SN 2006 AG, but this supernova didn't match the usual profiles linked to GRBs. Typically, long GRBs pair with hyper-energetic type I supernova, but this one was weaker and cooler, defying expectations. The burst's gamma-ray emission was also unusually soft, lacking the high energy punch of most GRBs. This weak output forced scientists to reconsider how they classify these events. Was it a failed GRB, a hybrid explosion, or something entirely new? Some theories suggest the progenitor star might have been less massive than usual, leading to a less violent collapse, while others propose that the jet responsible for the gamma rays was only partially successful in breaking free. GRB 060218 remains a puzzle, reminding us that the universe loves to throw curveballs. Its peculiar traits challenge our models and highlight how much we still have to learn about stellar deaths. Up next, we'll explore another cosmic rebel, a GRB that erupted far from its host galaxy's center, defying another set of expectations. Shifting our gaze to another cosmic enigma, let's unravel the mystery of GRB 070125. This wasn't just any gamma-ray burst, it was a powerhouse, radiating energy at a redshift of 1.547, placing it billions of light-years away. But what truly baffled astronomers wasn't its distance or intensity, it was its location. Unlike most long GRBs, which erupt in the star-forming hearts of galaxies, this one detonated far from its host center, out in the galactic outskirts where massive stars are rarely born. This odd placement threw a wrench into long-held assumptions. GRBs were thought to be born in dense stellar nurseries where short-lived massive stars collapse. Yet here was GRB 070125 flaring up in a cosmic no-man's land. How did its progenitor star end up there? One theory suggests it might have been hurled outward by gravitational interactions, a stellar exile meeting its explosive end far from home. Another idea proposes that star formation could occur in unexpected, isolated pockets of galaxies, invisible to our telescopes. The burst's afterglow offered few clues, leaving its origin shrouded in uncertainty. Its host galaxy, typical in size and shape, showed no signs of recent mergers or disturbances that could explain the star's remote location. This outlier forces scientists to rethink how and where massive stars and the GRBs they spawn can emerge. Perhaps the universe is more creative with its stellar factories than we imagined. GRB 070125 stands as a reminder that even our best models have blind spots. Up next, we'll examine a burst that played by the rules, a textbook example that confirmed what we thought we knew, only to reveal new layers of complexity. Now let's turn our attention to a burst that played by the cosmic rulebook GRB 120422A. At a redshift of 0.283, this gamma-ray burst and its accompanying supernova, SN 2012BZ, were so perfectly aligned with predictions that they became the gold standard for understanding nearby bursts. Unlike the puzzling outliers we've explored, this pair was a masterclass in cosmic predictability, confirming long-held theories about how these explosive events unfold. What made GRB 120422 a so textbook? For starters, its timing was impeccable. The burst's gamma-ray flash arrived right on schedule, followed by the expected afterglow, and just days later, the unmistakable signature of a Type I supernova, the kind linked to the collapse of massive, stripped-core stars. This sequence was a near-perfect match to the standard model, where a dying star's core collapses into a black hole, powering both the GRB's jet and the supernova's fiery aftermath. But the real triumph was in the details. Spectroscopic analysis of SN 2012-BZ revealed the telltale chemical fingerprints of a hypernova, complete with high-velocity ejecta rich in nickel and iron, exactly what models predicted for a GRB supernova duo. Even the host galaxy checked all the boxes, a modest star-forming dwarf galaxy, typical of environments where massive, fast-burning stars thrive. Yet even in its simplicity, GRB 120422 are offered subtle lessons. The supernova's brightness was slightly fainter than some models expected, hinting at variations in how these stars explode. And the burst itself, while energetic, wasn't record-breaking, a reminder that not all GRBs need to be extreme to be enlightening. This cosmic pairing proved that sometimes the universe follows the script, giving scientists a reliable benchmark to test against the more bizarre bursts we've encountered. Up next, we'll dive into a GRB that left behind a dusty trail of clues, revealing secrets about the interstellar landscapes of the early universe. Now let's shift our gaze to a burst that left behind more than just light, GRB 140518A, a cosmic event that turned interstellar dust into a treasure trove of clues. Unlike the textbook perfect bursts we've seen, this one offered something far more subtle yet equally revealing, a fingerprint of the dusty environments that filled the early universe. What made GRB 140518 a standout wasn't its raw power, but the way its afterglow interacted with the space around it. As the burst's light traveled through its host galaxy, it scattered off vast clouds of dust, creating a unique spectral signature. This wasn't just any dust, it was a mix of fine grains, some silicate-rich, others carbon-based, painting a detailed picture of the materials floating between stars billions of years ago. Scientists pored over the afterglow's fading light, noticing something peculiar. The way certain wavelengths were absorbed and re-emitted hinted at dust particles far smaller and more abundant than those in our modern Milky Way. This suggested that the early universe's interstellar factories were churning out dust differently, perhaps faster or under more extreme conditions than we see today. But the real surprise came when they compared this dust to other distant GRBs. While most bursts show similar scattering patterns, GRB 140518A's dust had a distinct blueness in its scattering profile, a quirk that defied simple explanations. Some theorized it could point to exotic grain shapes or even unknown dust-forming processes in young galaxies. This burst didn't just illuminate the cosmos, it illuminated our understanding of how the universe's building blocks evolve. By studying these dusty echoes, astronomers gained insights into how early galaxies enriched their surroundings, seeding future generations of stars and planets. Up next, we'll explore a landmark event that finally tied short gamma-ray bursts to their elusive origins, solving a decades-old cosmic mystery. Now let's turn our attention to a burst that rewrote the rulebook for short gamma-ray bursts, GRB 050509b. This wasn't just another flash in the cosmic dark. It was the smoking gun astronomers had been waiting for, the first short burst ever to leave behind a visible afterglow. And that afterglow, it led scientists straight to a surprising culprit, an old, quiet elliptical galaxy, a place where massive stars rarely roam. For years, the origins of short gamma-ray bursts were shrouded in mystery. Unlike their long-duration cousins, which scream massive star collapse, short bursts kept their secrets tight. Theories pointed to neutron star mergers, but without afterglows, proof was elusive. Then came GRB 050509b. At a redshift of 0.225, its faint afterglow flickered just long enough for telescopes to pinpoint its home, a galaxy devoid of the young, blue stars typically linked to GRBs. Instead, this galaxy was packed with aging red stars, the kind that hadn't birthed a massive star in billions of years. The implications were huge. If short bursts could emerge from such ancient stellar neighborhoods, their engines likely weren't dying massive stars. The evidence pointed squarely to compact object mergers, neutron stars spiraling together in a violent embrace. Here was a galaxy where star formation had long since fizzled out, yet it hosted one of the universe's most energetic events. That mismatch was the clue astronomers needed, but the surprises didn't stop there. The burst's host galaxy was also remarkably dust-free, unlike the messy, star-forming galaxies favored by long GRBs. This clean environment let the afterglow shine through unobscured, offering a crisp snapshot of the merger's aftermath. It was as if the universe had handed scientists a controlled experiment, isolating the signal from the noise. GRB 050509b didn't just solve one puzzle, it opened a new chapter in cosmic detective work. By tying short bursts to old stellar populations, it confirmed that the universe's most compact objects could unleash titanic energies long after their host galaxies had settled into retirement. Up next, we'll examine a burst so faint it nearly slipped through the cracks, yet its dim host galaxy revealed another piece of the GRB diversity puzzle. Now let's shift our gaze to a burst that defied expectations by calling one of the universe's dimmest neighborhoods home, GRB 080517. At a redshift of 0.089, this burst didn't just challenge assumptions about where gamma-ray bursts could occur, it practically rewrote them. Its host galaxy was so faint it barely registered against the cosmic backdrop, a whisper in a universe of shouts. This wasn't just any dim galaxy. It was a low-mass metal-poor system, the kind of place astronomers had long dismissed as an unlikely GRB factory. Conventional wisdom said gamma-ray bursts, especially long ones, favored bright, star-forming galaxies bustling with heavy elements, but GRB 080517 begged to differ. Its host was a cosmic underdog, a galaxy so unremarkable it would have been easy to overlook, yet it produced one of the universe's most extreme events. The implications were profound. If a GRB could ignite in such a faint, metal-deficient environment, it hinted at a hidden diversity in the conditions that spawn these cosmic explosions. Perhaps the early universe, teeming with similar small, pristine galaxies, was an even richer GRB breeding ground than we thought. Or maybe the lack of heavy elements in these systems actually favored the formation of the fast-spinning, massive stars that power long GRBs. What made this burst's host galaxy especially puzzling was its metal poverty. Heavy elements forged in stellar furnaces and scattered by supernova were thought to play a key role in GRB formation. Yet here was a burst thriving in their absence. It was like finding a skyscraper in a desert, proof that nature's rules are more flexible than we imagined. GRB 080517 didn't just add another entry to the GRB catalog. It forced astronomers to broaden their search, to consider that the universe's most luminous explosions might lurk in its quietest corners. Up next, we'll witness a burst that put Einstein's theory to the test, with photons racing across the cosmos at speeds that could have rewritten physics itself. Turning our attention to a burst that became a cosmic speedometer, let's unpack GRB 090510. This short gamma-ray burst, located at a redshift of 0.903, didn't just light up the universe, it put Einstein's theory of relativity to the ultimate test. What made it extraordinary wasn't just its energy, but the precision with which its high-energy photons raced toward us, arriving within milliseconds of each other across vastly different wavelengths. Here's why that timing mattered. According to Einstein's special relativity, all light, no matter its energy, should travel at the same speed in a vacuum, the cosmic speed limit we call the speed of light. But some theories of quantum gravity suggest that at extremely high energies, photons might actually experience spacetime differently, causing subtle delays. GRB 090510 became the perfect experiment to check this. Its highest energy photon, a staggering 33 billion electron volts, arrived within a fraction of a second of its lower energy counterparts. The implications were profound. That near-perfect synchronization was a resounding vote of confidence for Einstein's century-old theory. If high-energy photons had lagged even slightly behind, it could have hinted at cracks in relativity or evidence of quantum gravity effects. Instead, the burst's clockwork precision suggested that spacetime remains smooth and consistent even under extreme conditions, at least down to scales of 1 part in 10 to the 17th power. But GRB 090510 wasn't just a physics lab. Its short duration, just 2 seconds, also reinforced the growing link between compact object mergers and short GRBs. The burst's properties, from its lack of an associated supernova to its host galaxy environment, pointed to a neutron-star collision as the likely culprit. In one brilliant flash, it connected the dots between stellar deaths, gravitational wave sources, and the fundamental fabric of spacetime. This burst didn't just illuminate the cosmos, it tightened the chains on our understanding of physics itself. And as we prepare to close this journey through the universe's most distant gamma-ray bursts, one final revelation awaits. A glimpse into the future tools that will push our search for these cosmic beacons even deeper into the unknown. As we stand on the brink of a new era in cosmic exploration, the hunt for gamma-ray bursts is about to leap forward with groundbreaking technology. The Vera Rubin Observatory, set to begin its legacy survey of space and time, will scan the entire visible sky every few nights with unprecedented sensitivity. This means catching the faintest afterglows of distant GRBs that current telescopes might miss bursts from the very edge of the observable universe. Then there's the James Webb Space Telescope, with its infrared eyes perfectly tuned to peer through cosmic dust and spot the host galaxies of high redshift GRBs. While current observatories struggle to see galaxies beyond redshift 10, Webb could reveal bursts from the first 500 million years after the Big Bang, potentially uncovering population Roman 3 stars, the universe's very first stellar generation. But the revolution doesn't stop there. Upcoming missions like the European Space Agency's Theseus satellite will specialize in catching early X-ray signals from GRBs, while gravitational wave detectors like LIGO and Virgo could soon pinpoint the mergers behind short bursts with even greater accuracy. Together, these tools will create a multi-messenger network, allowing us to study GRBs across the electromagnetic spectrum and beyond. Perhaps most exciting is what we might discover by accident. Every time humanity builds a more sensitive instrument, we find cosmic phenomena we never predicted. The next generation of GRB hunters could reveal entirely new classes of bursts, ones that challenge our understanding of stellar deaths, spacetime, and the limits of the observable universe. The story of gamma-ray bursts is far from over. With these tools now coming online, we're not just preparing to observe more distant bursts, we're getting ready to rewrite the textbooks on the early universe itself. Now, as we bring this cosmic journey to a close, let's take a moment to reflect on what we've uncovered. Over these 50 incredible facts, we've seen how gamma-ray bursts, especially the most distant ones, act as cosmic lighthouses, illuminating the darkest corners of the early universe. From GRB 090423, the farthest burst ever detected, to the mind-bending energy of GRB 080916C, these explosions have revealed the violent births and deaths of the universe's first stars, the distribution of primordial metals, and even the conditions of the cosmic dark ages. We've explored how telescopes like Swift and Fermi catch these fleeting events, how afterglows serve as time capsules, and why some bursts defy classification altogether. Distant GRBs have challenged our theories, surprised us with their power, and even hinted at the existence of population Roman 3 stars, the elusive first generation of celestial giants. And with next-generation tools like the Vera Rubin Observatory and the James Webb Space Telescope, we're on the verge of uncovering even more secrets buried in the depths of space and time. So what's next? The universe is full of mysteries waiting to be solved. Maybe it's the enigma of fast radio bursts, the nature of dark matter, or the search for life beyond Earth. That's where you come in. Let us know in the comments what cosmic puzzle should we tackle next. Don't forget to like this video, subscribe for more deep dives into the universe's greatest wonders, and hit the notification bell so you never miss an exploration. Until next time, keep looking up.